As computer graphics professionals, we must not only know how the human eye works, but also how digital computers encode information. Our eyes are but one component of the human vision system. They allow us to collect information, or light, from approximately 400 to 700 nanometers and pass that information to our brains where we perceive color stereo vision. When light from an object reaches our eyes, it is focused at our retinas by the cornea and the lens. The retina is covered with photoreceptors called rods and cones. Uniformly distributed throughout the retina, we find approximately 130 million rods, which are responsible primarily for picking up luminance information. This is what allows us to see at night. This is what allows you to see your black and white world. Within the center of our retina, we find a region called the fovea. This part right here has three different types of cells, which we call collectively as cones. But there's three different types within there. There are some that allow you to see red, some that allow you to see green, and some that allow you to see blue. After our eyes collect the information, it is sent to at least 6 different portions in our brains. Along the way, the information is processed. We don't have one nerve per sensor in our eyes. So what actually arrives at our brains is less than the information that we collected. Armed with this knowledge, we can look at how to represent color information digitally. We're specifically going to be looking at how to use the RGB color model to represent color information. Within this model, what we have is 3 primary colors, the colors red, green, and blue. We call those our primary colors, and every other color can be made up of those. Mathematically, we can view this as being a vector space in R3, that is 3 dimensions, where our primary colors form our basis. In practical terms, we can think of this as being 3-dimensional space, but instead of having an X dimension, a Y dimension, and a Z dimension, you have a red, green, and blue dimensions. So X might be red, Y might be green, and Z might be blue. Really, whichever goes with which doesn't matter as long as you have 3 dimensions, as long as you have 3 independent things that we can add, in this case, red, green, and blue. With this vector spacing R3, we can represent any color that we can see as a vector within the space. The coordinates for our vector designate how much of our primary colors are within that. For example, if we wanted to designate the color yellow, well, the color yellow is 100% of red, so we would take 100% going up the red axis. We would then take 100% going down the green axis, because the color yellow is red at 100% plus green at 100%. And as you see here, the resultant would take you to the color yellow. So the coordinates of the color yellow would be 1, 1, 0. Now within computer terminology, we typically adopt a scale that goes from 0 to 255, and that's because we usually allocate 1 byte per color. Therefore, our scale typically goes between 0 and 255. Therefore, our color yellow will not have the coordinates 1, 1, 0. Instead, it's going to be 255, 255, 0. Okay? Well, now that we have this cube, as I mentioned, let's see, well, why is it a cube? How do we get a cube? Well, if we plot out the rest of our primary colors, both in the additive domain and the subtractive domain, you will notice that it is in fact a cube. At 0, 0, 0, that is the absence of any color, we're going to find the color black. All the way across from that, at 255, 255, 255, we find the color white, and that basically means add green at 100%, add red at 100%, add blue at 100%, and that will put you the color white. And then at the other locations, you are going to find the colors cyan, yellow, magenta, red, green, and blue. So as you see here, now we actually do have a cube, and within this cube we can plot out vectors that designate any possible color that we can think of. Within our model, we say that our primary colors are linearly independent because it would be impossible to create any one of the colors from the other two. For example, it would be impossible to create the color red by adding any amount of the color green or the color blue. Geometrically, we can see that the vectors that define green and blue form a plane. Regardless of you add these two vectors, it will be impossible to generate a third vector that includes any red. All possible vectors that you could generate will lie on this plane. To generate any vector that has any amount of red in it, you would need a vector whose head was not on the plane. And this is just not possible. We can also see this relationship by looking at the scenario algebraically. What we seek are two values, a value for A and a value for B that would satisfy this equation. A is the amount of green that we would like to add, and B is the amount of blue that we would like to add. As you can see, as we simplify this equation, it would be impossible to find any A or any B that would actually give us an equation that works. As we have seen, our algebraic explanation matches our geometric conclusion.